So.
Yeah, I'm sorry.
That's what I realized. So just a couple of notes in the homework 3. Most of you got the answers right, the derivation correct. Couple of you made a critical mistake. So the first one was pretty straightforward. We did it in class. All you have to do is use the integral v dot dl equal to mu naught ni, and you can figure out the b field is going to be equal to mu I divided by 2 pi r. So that derivation is pretty straightforward, starting off from Maxwell's equation. This one is not as straightforward as the first one, because there are a couple of things that we can't assume here. First, we can't assume the B field here is going to be the same as B field here. B1 definitely is not going to be equal to B2 in magnitude. In this case, it would fail because of symmetry around the center point that we chose. Right? We put the circle, we put the conductor right in the middle of the circle. But in this case, the length varies. So B1 is definitely not equal to B2 in magnitude. And the second thing is B1 and B2 directions are not going to be the same. Right? So B1 is along this because it's perpendicular. So if you draw an inscribed circle, it's going to be tangential to the circle. B2 is going to be tangential to the another concentric circle. Right? So it's going to be tangential to the circle, but not tangential to the line. So when you do integral b dot dl, the dot product means you can only take component if you have a curve like this and you have some B field like this. Only the tangential component of the B field matters, right? Not the perpendicular component. This doesn't matter for the line integral. So you need to figure out what the B field at this point is going to be. You can take some random. If this is radius r and this is some length L, this is going to be square root of r squared plus L squared. Going back to this formula, replace r with square root of r squared plus L squared. You can figure out what the B magnitude is, and then take the cos theta of it to get the component along the line that you had. Right? And again, theta you can just get from this. So, and then once you do that, then integrate it from for the whole square that you have. Right? So it's not straightforward. You can't just directly say, hey, it will be dot dl is going to be mu naught I. That's what is required to be proved. So the couple of you who made a mistake there, you can correct it and resubmit it, but otherwise, rest of you got it absolutely fine. I have posted homework 4 a bit sooner because the first 2 questions of homework 4 were supposed to be in homework 3. Pretty straightforward. First question is just derivation of what I did in class, redoing it. And the second question is just using the formula to find out the inductance and stuff like that. But the rest 3-4 problems will take a bit of time, so do start early. Okay. So, anybody have any questions with the homework? So last class we covered a lot of prerequisite electromagnetic theory content. So this class, let's try and do some couple of examples to get a hang of how what things are. And going forward, we are going to be covering new content in this course. All the prerequisite content is done. So I will be going slowly. If at any point, if you feel like go a bit fast, just stop me. Right. Yep.
Will the exam cover homeworks 1 through 4 or 1 through 5?
1 through 4. I know that there will be no homework the next week. And we'll give time for you to prepare for the exam. So, going forward, these are the 4 equations that we need. Right. So we define the term flux. Flux is the surface integral of B dot ds. If the B is perpendicular to the surface area and it's constant across the surface area at any given particular time, it can vary in time, but for a given time it should be constant. Then you can just replace the integral, which is B times the cross section in the surface area, or these are the consideration. And if you try to do the same thing for a closed surface, that value becomes 0 because whatever flux goes in must be the flux that leaves out because of there are no magnetic monopoles. Right? Going forward, this is the only expression that we need to remember. So the first equation, we don't need to remember the Maxwell's form of it, nor do we need to remember curl and divergence, none of those. So the second equation that we have to remember is this one. If you go around the loop, right, a closed loop and integrate the H field, again dot product, so the tangential component is the only thing that matters. It is going to be equal to n times the current in the conductor, assuming that there are n turns and all of the turns are carrying the same current I. Right? If there are 2 set of turns, if there is n1 turns carrying current I1 and 2 turns carrying current I2, all of that within that loop, then it will be n1 I1 plus n2 I2. Right? So this is n times the current in the conductor. And if you remember previous from to last week, this equation was n times the current enclosed. Right? We wanted to eliminate the current enclosed term because current enclosed can be current in the conductor as well as the current of the material or supposed material current that Ampere was trying to measure. And that introduces a bit of complexity. So we introduced a new term called magnetic field intensity, which is purely a function of the current in the conductor alone. And then we said we'll link this to the magnetic field using the BH curve, which is experimentally obtained for any material. Right? So that was the curve that we saw. So this is the BH curve. So this curve is experimentally obtained. So you put the material, you pass different amounts of current, basically controlling the H field, and then figure out what the measure what the magnetic field is, and that's how you end up getting the curve. And this curve is a bit tricky. It varies with the frequency in which you're doing this experiment and so on and so forth. So it's not as simple as the diagram I've drawn there, but for our case, for our course, we will be the way. And if you are in the linear region where H field, the H is very low or the current is very low, then when you have a material like iron, the relative permeability comes out to about 6,000. And when the iron saturates, when you go deep into saturation where you put a lot of current, there are no more domains to be aligned, then the iron starts to behave exactly like air, which has a relative permeability of 1. All right. So this relative permeability is a unitless quantity that multiplies onto the mu naught term. Right. So it's not it doesn't have any unit to itself. Okay, and then the final two equations, we have the EMF equation straightforward from Faraday's law, E equal to negative n d phi by dt. The negative comes from the length thing, and then is the number of turns. Flux phi is the flux that's changing in each turn that we have. And the final equation is forces L times I cross B. Different people like to put it in different forms. Sometimes you'll see in textbook I times L cross B. It's purely a matter of convention whether you want to assign a direction to current or direction to length. I choose current, so it's L times I cross B. Right? You have any questions so far? So going forward, these are the only 4 equations we'll be using for this lecture as well as any machine. When we go to DC machine design and stuff, we'll be relying on these set of equations alone. So let's start off with a very simple example. So let's say I have a current carrying conductor and I want to figure out what the magnetic field is at some length R equal to 10 centimeter. Can you very quickly tell me what the formula is going to be? Anyone?
mu naught I enclosed over 2 pi r.
Thank you. Mu naught I enclosed divided by 2 pi r. In this case, it is purely air gap. There is no magnetic material of any sort. So I enclosed is just I conductor for this case. Okay, so if you substitute those values, mu naught is 4 pi, 10 to the power minus 7, conductor current is 10 ampere, divided by 2 pi, divided by 10 centimeter, it's going to be 0.1 meter. If you solve all of these, this should come to about 20 into 10 to the power minus 6 Tesla or 20 micro Tesla. Right? This is very small because in a motor, typically, if you look at the air gap, you would want a magnetic field of around somewhere between 0.5 to 1.2-ish Tesla. So we are 10 to the power minus 6 less than 10 to the power minus 5 lower than the intended value that we want to get to. So air gap has this very bad property where it's not a ferromagnetic material, so it doesn't amplify the magnetic field. So we typically want to put this thing inside some kind of magnetic material so that the magnetic field can be much, much greater. To give a reference to this value, if you look at the Earth's magnetic field, which is pretty weak, is around 0.3 to 0.5 Gauss. Varies at different locations and throughout the year it varies too. There is roughly taking the upper limit that comes to about 50 micro Tesla. Right, so just a little bit distance away from a current carrying conductor, the B field dives to a very low value that it's not even comparable to the value of the magnetic field of Earth. So what we do is we use this kind of arrangement where we have some kind of ferromagnetic material, in this case again silicon steel. So this is an ideal case where I use like a solid block of silicon steel. In reality, this is not how we'll do it. We'll take thin elements of this kind of C core, right? Just a thin plate, which is then laminated so that the plate does not conduct any current, just to prevent something called eddy current losses, which is one of the core magnetic losses we'll look at later. But we'll take these thin plates and stack them up all together to form this big core that we have. Same thing we'll do with motor. It's not a solid iron block. It's stacked up steel plates that we have, right? Silicon steel plates. So for our case, again, let's just consider it to be a solid block. And the permeability we are going to consider for this core to be pretty high. So we are not going to assume saturation. So no saturation. Throughout this course, there will be rarely one or two places where we'll look at saturation, what happens, but otherwise we don't need to care about it. And then there is this tiny air gap that is separating these two iron sites, right? Otherwise, it's a full iron core. And we are going to pass some current through this coil, and we are going to figure out what the magnetic field is in the air gap. Okay. So this is something similar to what we are going to be doing later when we go to motors. We have our stator, and then we have our rotor, and in between there is some air gap. And through that air gap, some B field power goes through the air gap, and through the air gap is what energy transfer happens from the stator to the rotor by using the magnetic field. Yep, John.
Is there any significance? I noticed the subscript there is C instead of R. Does that mean anything, or is that just?
Oh no, I'm just using a subscript C because later I'll use another subscript just for core. So C indicates the core iron core.
Right.
Okay. Yeah, just the same as mu R. Depending on when I use a magnet, I'll put mu M. When I use air gap, I'll say mu G, which is 1, and so on and so forth. Any questions? Okay, so I've given all the dimensions for it. So let's go ahead and look at how we'll figure out the values for the BG in the air gap. So anybody want to start off? What if I had given this problem as a homework without doing it in class? How would you have started? Everything that you need is on the left-hand side of the board. And the last two equations are irrelevant for it. There is no force we are interested in. We are only interested in the B field in the air gap. We are not interested in the EMF of this coil. I've already given you the current. Right? If I've given you the EMF and asked you to figure out the current, that will be a bit more complicated problem, but I've already given you the current. So last equation is irrelevant too. There are only two other equations, so maybe you want to take a guess. Yeah.
Would you do the magnetic field intensity equals Ni?
Okay. So for that, before we do that, we need to draw a loop, right? So you can choose any kind of loop. And depending on the loop you choose, the value that you get out of it is going to change. So we are going to choose a loop like this. Again, we will look at cases where we choose other loops too and see what would happen to the result. So in this 2D diagram, it's going to be this particular loop. So if I go around this loop and integrate the H field, integral H dot dl is equal to N times I conductor. And our N was 100, our current in the conductor was 200. What happens to this term? What do I do about the term? Anybody? So let's assume the magnetic field inside the core is HM and the magnetic field in the air gap is HG. Right? There is no reason that HM needs to be constant throughout the length of the core, but for now, for simplicity, let's assume that HM is constant, and later we'll prove that HM will remain the same across the length of the core. All right, same thing with HG. In the air gap, there is no reason when you pass through the length of the air gap, HG needs to be a constant, but we'll later prove that it will remain a constant, it won't vary that much. All right, so for now, take it for granted that HM and LM are constants across the length. So then we can pull it out of the integral. So we have HM, LM, I'll get to what LM is in a second, plus HG, LG equal to N times I conductor. Okay. So LG is the length of the air gap, which is given here, 0.2 centimeter or 2 millimeter. Typically, when you have a motor, the air gap thickness is about 0.5 millimeter to about 2 millimeter. Extremely tiny length, and we'll see the reason why it has to be small enough. And we have taken the upper limit for this example. Okay? And LM is the total length of the design core. So this side plus this side, plus this side, plus this side, plus this side. All right, so it's going to be this 10 centimeter plus 15 centimeter, and then this total length is going to be 10 centimeter plus 10 centimeter plus 0.2 centimeter, and then again 15 centimeter plus 10 centimeter plus this 0.2 meter. All right, so that's what this LM is. So this is the mean core length. So there is going to be the 15 centimeter on the bottom, and then on the left hand side it's going to be 10 centimeter plus the 0.2 centimeter plus the 10 centimeter. This is for the left. This is for the bottom, and same thing for the top as well. So let me just do 2 times. And then on the right hand side, it's going to be 10 centimeter plus 10 centimeter without the air gap included, because air gap length is accounted for here. Right, so it's going to be 2 into 10 centimeter for the right hand side. Then LG itself is given as 0.2 centimeter. So these are values that we have. Everything is known here except for HM and HG. Right, so we have 2 variables but 1 equation. What do we do next? What was it?
Substitution.
Substitute what with what?
You could solve for one of them, or like solve it as a factor of one of them. And then
Alright.
plug back in.
Yeah, but the problem is we only have just 1 equation here, right? So you can represent HM in terms of HG, that's absolutely fine. But then what do you do? Yep.
I have a question.
Yeah.
So on the left, you don't have the air gap, so that's 2 times 10, but on the right, the air gap, so that adds length. Would they not be the same, or I don't know?
Oh yeah, so here, right? So the left hand side length is exactly the same as the right hand side length. So 10 plus 10 plus 0.2. Right? On the LHS, that's what I have here. When we come to this side though, the iron core is only this 10 centimeter and this 10 centimeter. In between there is an air gap, so we're not including that 0.2 centimeter. Right? That 0.2 centimeter comes in this LG term.
Oh, okay. Oh, okay, I get it.
Right? So this is 10 centimeter. So on this side, this is going to be 10 centimeter. And then this top part is also going to be 10 centimeter. And in between also there is iron on the left hand side. Right? On the right hand side, there is an air gap, so we are not including in the right hand side the 0.2 centimeter. Right? Any other question? Okay, so what do we do for the solving this? This is definitely a solvable solution, solvable problem. So let me only use 1 equation, right? But we do have 1 more equation on the board there. So we have integral B dot ds is equal to, so if I take a closed surface and apply integral B dot ds, that is going to be equal to 0. So let me start off with the closed surface here. I have different choices, so let me create like a closed box. Mathematically closed box here, right? If I apply the fundamental theory that if I go over the surface and integrate, the B field is going to be 0, that essentially says whatever flux enters on the LHS left hand side must be equal to the flux lines that leave on the right hand side. Right? That's what this says. So whatever comes in must be the same thing that goes out. Here that information is totally useless because we have already made that assumption that HM on the left hand side is same as the HM on the right hand side, right? So what we have basically done here when we did that assumption, when we said HM is constant in the core, what we are saying is if I look at the flux coming in, it's going to be the same as the flux going out. So that means, let me say this one is B1 on the left hand side, right side is B2. And let's say these two cross-sectional areas are exactly the same A. So B1A is equal to B2A, right? Because the B field throughout the length is going to be constant. In that case, I can apply just the formula B times the cross-sectional area. So A cancels, so B1 equal to B2. If B1 equal to B2, then H1 equal to H2, right? Because B1 and H1 is related just by the factor of a scaling factor mu1. So that's the reason in this case, when I started off, I said throughout the core, the HM is always a constant. HM is not changing. I can do the same for the air gap. I can put a box within the air gap and say whatever a B field is coming on the top, the flux coming on the top must be the same flux leading in the bottom. So there will be the same thing here again, B1A equal to B2A, B1 will become equal to B2. That means again H1 will be equal to H2 in the air gap as well. So across the air gap, Hg is also going to be a constant, which is what we used in the previous assumption. But if we instead draw a box that encompasses a portion of the iron core and a portion of the air gap, right? This formula would still hold, right? It's a fundamental formula. So whatever flux comes from the top side must be equal to the flux that leaves on the bottom side, right? What is the flux coming from the top side? If Bm is the magnetic field in the iron core, and Bg is the magnetic field in the air gap, what is going to be the flux coming from the top side?
Bm times A.
Bm times A. So there is going to be the flux coming from the top side is going to be Bm times A. And the cross-sectional area, you can just figure that out. It's 5 centimeter times 4 centimeter. So let me leave it as just AM. AM being the cross-sectional area. Oh, sorry. Let me use the subscript C for code instead of M. Sorry. So Bm times A, BC times AC must be equal to whatever the flux is in the air gap, which is going to be equal to Bg times Ag. And so Ag and AC, you can assume them to be same if there is no fringing. So, but that won't be the case in reality. So in the iron core, the B field has a propensity to stay within the iron core, and because the path outside has a much higher reluctance. I'll get to what reluctance means. Think of it as resistance. So when you have a current carrying conductor, and there are two parallel paths for it to choose. Let's say this is 0.1 ohms and this is 1 mega ohms. The current is for the most part going to prefer going through the path with the least resistance. The same thing happens with the flux too. If there is an option given where it can pass through the iron instead of going through the air gap, it is going to prefer going through the iron. But once it encounters air gap, there is nothing constraining it to be within this vertical bounds that I have here. Right? After once it hits the air gap, it starts going through all available pathways through the air gap. So that is the reason when you have this magnet, an Alnico magnet in particular, inside the magnet, the field lines are vertically glowing from the south to north without fringing outside the material itself because it's highly ferromagnetic material. But outside, once it hits air gap, it has all the pathways are equally good for it, right? So it's like 1 mega ohm resistance in parallel with 1 mega ohm resistance. It's going to go through both pathways equally. So that's what happens once it hits the air gap. So the B field is not going to be constrained just in this vertical direction. It's going to spread around, and this is called fringing. And then it's going to spread back in, and once it encounters iron, again it has a preference to go through the iron instead of choosing to go through outside of the iron. Okay, so this is fringing. If we ignore fringing, you can use the formula AC equal to, yep, Thomas.
So does that mean the path length for the fringe magnetic field is going to be the same as the path length for the field that's going straight through? Because like, why would the magnetic field like decide, for lack of a better term, to like go a longer?
Oh, okay. So let's say I give you a resistor wire of let's say 1 meter, and then I give another resistor wire which is slightly longer. Right? Let's say this resistor wire is 1.2 meter, this resistor wire is 1 meter. Right? If you pass a current, some of it is going to split into this, some of it is going to split into this. Same thing would happen here. This kind of protruded path is slightly longer, right? But that's still a pathway for it to go through. So it is not that just because I have 1 ohm resistance, 1 meter wire, resistor wire, this is the shortest and the lowest resistance, all the current will go through it. It's always going to prefer the other path as well.
So then the magnitude will go down.
Which
Like
one?
the strength of the magnetic field. in
Yeah,
the
the
fringe.
strength of the B field will go down.
Okay.
In the airgap. Yeah. Any other question? Yeah, Chris.
So does that mean that, like, you were saying in the magnet, when you're actually in the car, all the magnetic field is in there? Is there technically some, on
There
the
will be
outside
some
that's-
field that will leak out.
but using your analogy, like, the resistance is so high on the outside that there's almost none?
Yep. So in case of so think of it like the core to be a wire and the air gap to be resistance. So when you have a current carrying wire, the current is going to try to stick within the wire. Right? That analogy is slightly off because in case of a current carrying wire like copper, conductivity is in the order of 10 to the power 6. Right? In this case, mu r is in the order of 10 to the power 3. So it is not as good as a copper wire. Right? And the bigger problem for electrical copper wire is not as way better conductor compared to the magnetic field conductivity of iron core that we have. And the second bigger problem would be once this core starts to saturate, the core will start to behave like an air gap. Right? At that point, all the field lines will start to leak through multiple different pathways. It will no longer have a preference to stick through just iron core. Any questions? So if there is no fringing, we can use this. If we are to consider fringing as well, so in the homework for the exam, I'll typically ask you to ignore fringing. But if you are asked to consider fringing, there is a rough estimate LG for the area of the air gap. So this is just a rough estimate that's been obtained by doing numerical simulations and figuring it out. What it looks like, you can't solve this by hand. You need to use some kind of finite element analysis when you consider these nonlinearities into picture. But a rough idea is, so if you have a tiny air gap, which is much smaller than the mean length of the iron, then you can assume that the field lines are almost 45 degrees at the edges. That means if this total length is Lg, this length is going to be Lg by 2, this width is going to be Lg by 2, and this width is going to be Lg by 2. And this is going to happen on all four sides. So what you're basically doing is this Lg by 2, this Lg by 2 becomes Lg, and you add it on to the width of the iron core, whatever the width of this iron core is. Right? This is the width, and let's say this is the length L or thickness L. So take the width, add the Lg by 2, Lg by 2, that becomes W plus Lg, and then again take this dimension, add Lg by 2, Lg by 2, that becomes L plus Lg. Right? That will be the area over which the B field spreads out. So that is just a rough thumb rule first order approximation. When you go to numerical simulation, you can do much higher order. But if there is fringing, you can use this going forward. So we have a couple of terms now available. So we have BC, AC must be equal to BG, AG must be equal to the flux, phi. So I can rewrite the magnetic field in the iron core as flux divided by the cross-sectional area. And then I can rewrite the magnetic field in the air gap as flux divided by cross-sectional area. Now I have two equations, right? I have this equation and I have this equation. Unfortunately, I have four variables. How do I solve it? Are they all four independent variables?
I was just gonna ask, so you divide flux by the area and you get the B field?
Yep. That's why it's called magnetic flux density, right? Flux per unit area. Yep. Yep.
AC and AG are the same,
AC and AG are what?
the same.
We can use the same or we can have it separate just to make sure that we are including fringing case as well. But the four variables that I'm talking about are BC, BG, HM, and HG. Right, so the four equations, the four variables are this BC, BG, HM, and HG. But we have two equations. Is it still solvable? Yep, Thomas.
Do you know the relationship between BC and H?
Yeah,
HG.
all HG. Okay. So we do know the relationship between HC and BC as well as BG and HG, right? That's the one that I've written right here on the first screen, where B is just mu R mu naught times H. And for the iron core, I've given the mu R to be 6,000. For air, I've given it to be 1. So there is a direct relationship between the B and the H, right? So we can just substitute those. So let's see. Our magnetic field in the core is just mu R, mu C times mu R times Hc, mu C times mu naught times Hc. So mu C is given as the relative permeability unitless quantity 6,000 mu naught 4 pi into 10 to the power minus 7. I think Henry per meter is the unit. Double check if it's Henry meter or Henry per minute meter. And then Hc. It's not the meter. Right? Same thing we can do for the B field in the air gap. That is going to be equal to just mu naught times Hg, because mu R, the relative permeability of air gap is just 1. So you can substitute those values. So this implies our Hc is Bc divided by mu C mu naught. And then this implies Hg is Bg divided by mu naught. This again implies it's equal to, we can substitute for BC as flux divided by AC. We have flux divided by mu naught, mu C, 1 by AC. And this again would be equal to same flux divided by mu naught divided by Ag, air gap thickness. So now we have resolved it into a single variable, right? We have expressed both Hg and Hc in terms of flux phi. So we got all the terms we have. We can just substitute them into our original first equation. So once you plug in those values, you can pull out the phi common, which is the flux term, and just substituting the values up there. So I have Lc from here divided by mu naught, mu C, Ac plus Lg, air gap length, divided by mu naught Ag is equal to n times I conductor. So everything is known here except for the flux, and you can solve for the flux. Right? So this term that we have there, this L divided by mu naught mu C Ac, is called the reluctance. This is a new term we are going to be introducing. Reluctance. So let's call this reluctance of the core Rc and reluctance of the core air gap Rg. So we can rewrite this equation in a different form. So flux times Rc plus Rg is equal to Ni. So if you look at this, this is exactly same as if we had a voltage source and some resistance for the wire and some actual resistance external, and close this. If this voltage was some V equal to value whatever Ni comes out to, and this resistance is same as the reluctance that we have there, then the current through the circuit I is going to be equal to V divided by Rc plus Rg, which in our case we are representing V as Ni divided by Rc plus Rg, which is same as our flux state. Right, so it's equivalent to what we have in an electrical network. So now it will start to make a bit more sense, because if you, in our case, if you look at this term, the denominator has this mu C in case of the iron core, and there is no relative permeability for the air gap. So if this value is very large, this reluctance becomes very small. That is same as in our circuit, when the conductance of the wire is very large, the resistance of the wire becomes very small. Right? And why we are looking at this equivalent network is, if I say, we looked at a very simple magnetic circuit, but let's say I complicate the magnetic circuit with multiple pathways for the flux. Right? If I had instead given you a magnetic circuit that looks like this, How will we go and figure out what the flux is going to be, what the magnetic field is going to be? Very straightforward. That is exactly same as putting another resistor in parallel, right? RG1, RG2. We know how to do current division. We know what the voltage across each of this would be, and so on and so forth. Right? So it's always easy to take the magnetic circuit that you have and visualize it in terms of an electrical circuit. So this term, flux, is equivalent to current. This term, we are going to introduce a new term called MMF, N times I, magnetomotive force. This is equivalent to REMF, electromotive force. Right? In the it's an electrical circuit case, the electromotive force moves the electrons. In our case, the magnetomotive force moves the magnetic flux. Right? So similar kind of concepts that we have there. Anybody has any questions to this part?
So then the current equivalent would be the flux,
What was it?
is like the current equivalent of flux.
If the current equivalent is flux. Yep.
Can you explain again how you got the equation for the air gap area with fringing?
Oh, yeah. So this is a magnetic field going outwards, and then it goes to the other surface and closes the pathway. But once the magnetic field lines enter the air gap, there is no reason for it to stay constrained within this rectangular structure that I have. So it can go all around. In fact, it can go like this, come back, go like this, come back, like all the way to infinity. Right? Every single pathway is going to take to go through. But what happens is farther the pathway, longer the pathway, more resistance to go through the pathway. Right? So all of these longer length means higher resistance to the pathway, higher reluctance. So for the most part, it will try to stay as close as possible, but it will be just the single route, but it will try to bulge a little more forward. So using finite element analysis, we can get an exact estimate for what the equivalent air gap surface area is going to be. Right? But the first order approximation is just looking at the initial field lines that are coming out alone, ignoring all the other extended pathways, and making an approximation that this field line has an equal choice of either going like this or going like this. So we are going to approximate that it goes at an angle of 45 degrees. If it goes at an angle of 45 degrees, and the total length from here to here, so it goes at 45, comes back at 45, this total length is Lg, right? So this length, this half length will be Lg by 2, then this length will also be Lg by 2. Okay. So if you assume this fringing half length is Lg by 2, on the other side also will fringe half length Lg by 2. So the total length, if this was W plus Lg by 2 plus Lg by 2, this dimension would have increased to W plus 2 times Lg by 2, which is W plus Lg. Same thing would happen on this side too, right? So here also it will fringe like this, there also it will fringe like this along this length too. So if this length is L, then the fringing is going to be L plus Lg by 2, Lg by 2, that's going to be again Lg. And the area is just the, assuming it's a rectangular structure, it will be W plus Lg times L plus Lg, right? Any other questions? Okay, so let's substitute the values and look at what the numbers come out. You can double check it when you do this for the homework. Let me just give you the answers. So our reluctance RC comes out to 10 to the power minus 4 divided by 0.002 mu naught. You can simplify further. I'm not a big fan of substituting and solving. Just leave it there. So Rg comes out to 10 to the power minus 4 times 0.002 mu naught. So if you look at the reluctance of the core, it is 1 by 20th of the reluctance of the air gap. In spite of the core length being extremely large, if you looked at the core length, it's about 30, 40, 50, 60, 70 centimeters, right? While the air gap was just 0.2 centimeters. So in spite of the core length being 100 times bigger than 1,000 times bigger than what we had for our air gap, it still has much lower reluctance because of the relative permeability being much higher, right? So that is our reluctance. Once you substitute The reluctance here, substitute the current, the flux comes out to 0.0026. Again, in the homework, don't forget the units, Weber, named after a German physicist. Can you tell me how we'll calculate the magnetic field B in the air gap? That's what we wanted to do, right? These are all just steps to get there. Now we have the flux, how do we get the magnetic field in the air gap?
Could you just solve for B and then convert it to H using the relative permeability?
Right? Can you share any answer?
I was thinking of the flux equation at the end, at the very top, you could integrate over the.
Perfect, thank you. So we have already substituted for B into H and H into B, and that's how we got the B. Right? We're not interested in what the H field is in the air gap, because H is just a purely invented quantity that we made, right? Just to explain away the material current, which we don't know how to measure properly, or there is no way to measure material current. So that's the reason H was introduced. So in most cases, you will not be interested in knowing what the H is. It has no physical relationship with the world. What we would be interested is knowing the value of the B field, because the B field, then if I put a conductor inside that air gap, that is going to experience a force which I can calculate using this formula. So the B is what really matters. That's what we are interested in. So to get the B, what we do is you have your flux already. As Ganesh pointed out, put it into your equation that we have there, assuming that the B does not change across the surface area. Okay, so flux divided by the cross-sectional area, which is going to be flux divided by the air gap cross-sectional area. And that value comes out to about 1.3 Tesla. Okay. Any questions so far? So let's try and complicate this problem a little bit further. So for now, we consider a very simple network with just a single air gap and single set of circuits. What is going to be the B in the iron core? If you ignore fringing,
Should be the same.
yep, it should be the same. Perfect. Because the flux was BC equal to BG. If I assume the fringing is not happening, then AC is same as AG, those goes away. So BC is just equal to BG. Okay? But going back to the question Thomas had asked, if we consider the fringing effect, then AG becomes larger, right? So the BG would end up being smaller than BC when fringing comes into picture. So let's look at another magnetic circuit. Let me just plot a 2D view alone, but it's a 3D structure that goes back as well. It has some thickness to it. So the same thing as before, the dimensions are all the same. None of those I'm changing. I'm now introducing, instead of the coil that I had before, I am instead cutting the iron core and putting a magnet in between. So this is a magnet. Let's consider it to be an Alnico magnet, Alnico 5. And then we have the same air gap as before, 0.2 centimeter. And we want to figure out what the magnetic field here is going to be. So magnets, it's a typically neodymium magnet, or we have Samarium-Cobalt, or we have Alnico. These are the most commonly used ones. So do you know anybody knows who first created the neodymium magnets? Who has a monopoly of neodymium magnets? China. Who created the first neodymium magnet? It was GM here in the US in 1980. GM and another Japanese company independently created neodymium magnets right here. Samarium-Cobalt was created in the 60s by US engineer working in US Air Force. And then Alnico itself was created in 1930s, again by a Japanese company. Typically in our motors, we would be using neodymium magnets because they have very high retentivity in the magnets and they have large coercivity as well. But one of the biggest problems with neodymium is that they are very brittle. Those of you who have played with neodymium, if you leave two neodymiums, they'll hit one another and break right away. Okay, they're extremely brittle magnets. And the other bigger problem is they get demagnetized quite easily with temperature. So typically around 300 degrees C, that's the Curie temperature, which is the temperature at which all the domains would get randomly aligned and they'll lose their magnetic field instantaneously. So if your motor heats up too much, and the other big problem is as the temperature, it's not only at this temperature, it will get completely demagnetized, but anything over 100 degrees Celsius, the B field will start to drop exponentially. So motors typically would run at very high temperatures. We put some cooling and stuff, but we want to push it to as high a temperature as possible. So the thermal requirement is reduced as much as possible. But this neodymium magnet always puts the upper limit where if it goes too hot, then the B field starts to collapse a lot. So way around it is we have Samarium-Cobalt with a little bit of air gap. The magnetic field comes to around 0.95 Tesla, but it can go up to 750 degrees C. So for motors that work at very high temperatures, right, we typically use Samarium-Cobalt used in most military applications where the temperatures can get very high and you still want the motors and everything to be working. And then Alnico itself, the magnetic field is very low, but again, the temperature can be quite high, 300 degrees Celsius. So for this example, let's consider an Alnico magnet. And there are different grades of Alnico, Alnico 5, Alnico 6, all the way from 1 through 8 or 1 through 9. We'll just consider this grade called 5. So how do we solve the same problem as before? How do we solve the magnetic field in the air gap BG? Anybody want to get started? Lily already gave the answer. It's the same step. What do we do? Yeah.
Start with the H field, the
Okay.
friction field.
So draw the loop for the path you're interested in. You want to pass through the BG. So if you go around, integrate the H field over this loop, it has to be equal to N times I conductor. What is the right hand side going to be in this case? This is rather counterintuitive, but whatever you're thinking is correct. What is the RHS going to be in this case? Is there any current carrying conductor in there? It's just a magnet circuit, right? We already said we are not going to be interested in the material current or whatever supposed material current. So this is purely conductor current. So this term is going to be 0. So let's start off with let's say the magnetic field intensity in the magnet is HM. Let's say the magnetic field intensity in the air gap is Hg. And for this example, just to simplify the problem, I'm going to assume a relative permeability of the core is infinite. All right. So the same as saying when you solve electrical circuit, you're taking a wire, you don't consider the resistance of wire just to simplify your circuit. The same thing we're going to do. We're not going to be worried about what happens here because there is going to be no MMF dropped in this magnetic circuit because the permeability is infinite, the relative permeability is infinite. That means the reluctance is 0. If the reluctance is 0, same as before. A current going through some resistance drops some voltage. In our case, flux going through some reluctance drops some MMF. If the reluctance is 0, then there is no MMF dropped in it, right? So the MMF is either here or here. So let's do this integral. It's going to be HM Lm, where Lm is the length of this magnet and Lg is the length of this air gap. So HM Lm plus Hg Lg is going to be equal to 0. Okay, so I have one equation, two variables again. What do I do for the second one? How do we solve the second equation? How do we get the second equation?
This kind of a question. Could we just directly calculate the flux in the magnet using BA because we know the magnetic field?
We do not know the magnetic field. How do you know the
I
magnetic?
thought it was like given by the
No, these are the values where we'll go and settle to, but
Oh,
it's not
okay,
the
okay.
values that will. That's what we are going to be looking at. Okay? But we do not know what the magnetic field is. In fact, it's rather counterintuitive for a lot of times. That the magnetic field will change based on what the length of the air gap is. Okay? So how do we go about? What's the other equation that we can use? Anybody? We just saw the example before, same example.
replace, use B equals the relationship between B and H?
Yeah, but that would come after we find out an expression for B, right? How do we figure out what the B field is?
Use the magnetic flux equation.
Okay, use the magnetic flux equation. It's just those two equations, right? There is no other option for us. So whenever you're given these problems, irrespective of whether it's a motor or any kind of complicated circuit, just figure out what the first equation helps you solve and then figure out what the second equation can help you solve. Okay, so if you use the second equation, all that it says is if I were to draw any kind of box, right, I can draw a box here. So whatever flux is entering this box is the same flux leaving the box. That means flux through the magnet must be equal to the flux in the core. And the same thing I can extend. Keep on putting boxes saying flux coming here is the same as flux leaving here, same as flux coming here is the same as flux leaving here. So flux through the core is same as the flux in the air gap. So if we substitute the values, Bm, Am is equal to Bg, Ag, or let me do the center step as well, Bc, Ac equal to Bg, Ag, right? So the core itself is not something that we are interested in at this point. The reason assume the relative permeability of that is infinite. All we are worried about is in this relationship linking BMAM with BGAG. And once we have this, then of course we can go back and substitute the other relationships that we have, which basically says, so let me express BG as BM AM divided by AG, right? BG itself is going to be equal to mu naught times Hg. So which implies Hg is going to be equal to Bm by mu naught times Am by Ag. I'm just rearranging all the terms. Now that I have Hg, I can go back and substitute it here. So HMLM is going to be equal to, when I take it to the right hand side, negative Hg Lg, which in turn, if I substitute these values, it's negative Bm Am divided by Ag times Lg, right? And if I take this Lm to the denominator from the right hand side to the left hand side, that becomes Lm Lg by Lm. Any questions? Yeah, Thomas.
Can you explain one more time why we don't care about BCAC?
So this value is BCAC is going to be same as BMAM. Right? The particular reason I considered Alnico will become clear in a second, because Alnico behaves more or less like a ferromagnetic material. So if I know the flux, if I know the B field in the Alnico material, that is going to be the same B field in the iron core as well.
Okay.
Right? And we are not, we have already ignored any MMF drop, so the ion itself doesn't change anything in the pathway.
Okay.
Right? So that's why we are not concerned about what this value is going to be. Any other questions? Yep.
Are you just discarding the mu naught because it's going to appear on the other side eventually?
Oh, no, I'm not discarding, sorry. That was a typo. Mu naught is, thanks. Any other questions?
What's the difference between the things with the M subscript and the C, like the core and the...
So C is the core. Anything to do with the core is C. Anything to do with the magnet has the subscript M. Or the C, and then the air gap is A, or G, sorry. Okay. So
I guess what's the difference between the core and the magnet? Oh, is the magnet like a separate piece?
it's a separate piece.
Okay.
So take a magnet and then you use this. So this is a separate entity. So I had this iron core before. I cut through the iron core and replace that section with the magnet there. It's completely different materials.
Okay.
Any other questions? Yeah. So now that I have everything in place, let me substitute all of these values. AM, AG, LG, LM, mu naught. Right, all of those are known. again, for this case, I'm gonna assume AM equal to AG just to simplify my life. I'm also ignoring fringing. And there's not too much of a bad approximation either, because if you look at the width, it was 4 centimeter. And then LG itself was just 0.2 centimeter. And then the other one length was 5 centimeter. And then again, LG was 0.2 centimeter. So this is going to be 20 centimeter, and then these products are just going to be so small enough that you'll probably end up like, instead of 20 centimeter square, you would end up, if you assumed all of those values, you'll end up like 21.2 centimeter square or something. So we won't be too off in our calculation, ignoring the fringing effect. Right? But again, in the homework, if I don't tell you to ignore, do consider, for the most case, I will ask you to ignore it too. Okay, so once you compute all the values, your HM-VM relationship comes out to VM, don't have it. So HM is going to be minus VM by mu naught. AM AG is 1, 1. What was our LG? I have no idea. Oh, magnet LM length, that was 1 centimeter. So magnet length is 1 centimeter. So LM is going to be, LG is 0.2 centimeter divided by 1 centimeter. So that becomes a factor of 5. So our DM is going to be negative 5 times mu naught times HM, right? Once we substitute that comes out to roughly 6, number ahead, 6.28 into 5 minus 6. Minus 6 times HM. Alright, so all I'm doing is just basically substituting the values out. So once I have this, how can I solve for BM? Anybody want to take any guesses? Yep.
I have a question. Just conceptually, I don't understand why the rest of the loop, the rest of the core would not be interacting to impact PM.
So when you have, let's say, let's look at an equivalent electrical circuit. So let's say I have some source, and the source has some resistance, Rm, right? And then I'm connecting this to a wire, which has very low resistance, R wire, of very close to the order of 0.0001 microohms or something like that, right? And then I have some load resistance, which is represented by Rg. So if this value is very small compared to both Rm and Rg, then I can ignore it, saying that this is not going to impact my flux in any way, or impact the current in any way. Right? So the same thing happens here. In that case, we are assuming copper has infinite conductivity. In this case, we are assuming that the core has infinite permeability. So it's not going to drop any amount of local. Any questions? So once we have these, anybody want to take a guess as to how we are going to solve? How we are going to solve for what the B is going to be? So let me draw the BH curve for an Alnico magnet. So if you look at the relationship between HM and BM, it's a negative sign, right? Whatever HM is, BM is going to be negative of it, or BM is positive, HM is going to be negative of it. So what happens on the RHS really is not important for us. HM. So this is the BH curve of an Alnico 5. On the RHS, the second quadrant, in the non-dotted line, solid one is for neodymium. Okay. Both of it has a retentivity of about 1.25, more or less, Tesla. But when I wrote this value here, I said that the retentivity of the magnetic field you can get in a typical air gap with the Alnico 5 is around 0.4 Tesla. The problem is the way we solve this equation is if you have the relationship Bm equal to some value times Hm, let's plot how the curve looks like. Right, so this is going to be a straight line. Bm is equal to some negative slope, which is 6.28 10 to the power minus 6 times Hm. Right? This is the same as if I give you an equation y equal to mx. In this case, the m is just a negative value. Right? So it's just going to be a line with a negative slope. So the manufacturer will give you this data sheet which has this BH curve, and then depending on what air gap you have, the value changes because Hm, if you saw, there was a function of what the air gap length was. Okay? So depending on your circuit, this line slope is going to change. If you have a very large air gap, the slope is going to come down. So because the relationship was Hm equal to right here. Right? So this relationship, so we have it in terms of Bm, Hm there. Let's flip it around. So that's mu naught, negative mu naught Hm times Lm by Lg, assuming there's no fringing for simplicity. So if Lg becomes very large, right, the slope is going to come down and down. This is called the load line of our magnetic circuit. So this is how our circuit behaves, but this is how the magnet behaves. So what will be the value for the B? How will we figure out where the value of the B is going to be? When you have two equations, the way you solve for solution of two equations, right, we're using graphical methods. You plot the first equation, plot the second equation, the point where they cross over is the solution for the circuit. So this is the point where it will go and settle down. And if you look at what this value comes out to, in this example, it comes out to around 0.38 Tesla. Right? So this is what happens in an Alnico magnet, where even a tiny amount of air gap, the magnetic field will drop significantly. So the larger the air gap, the magnetic field will start to reduce further and further. This is not the case with neodymium magnet. So if you look at the case of a neodymium magnet, it has a very large coercivity. So the line goes for a very, very long distance. So in case of Alnico, this was negative 50 kiloampere per meter. In case of neodymium, that goes to about 950 kiloampere per meter. Right, the H field value. So it takes a very, very large amount of coercivity, large amount of current in the other direction to demagnetize a neodymium, but that's not the case with Alnico magnet. That also means, so whatever is the retentivity, that is really not of importance. Because even at the tiny amount of air gap, the field is going to drop significantly. So you all would have witnessed this firsthand, those magnets that you get from state parks, right? Those are all Alnico magnets because neodymium is quite expensive. So they just put these Alnico magnets. And when you stick these magnets onto your fridge, you'll know that they are stuck pretty tight. Right? It's very hard to remove them. But the minute you just remove them, even a slightest amount of air gap between the fridge and the magnet, it will feel as if you're holding paper. There is no force attracting it. Right? Because all it requires is a tiny amount of magnet and the magnetic field just plummets almost close to zero. And this is the same problem that happens when you have these magnets. So how many of you have seen a horseshoe magnet? No. So whenever you see these magnets, you'll see that there is a plate covering the top of the two poles of the magnet. Right? There is a reason that this magnet is shaped like a horseshoe, because a typical magnet, the bar magnets that we see, if you have a magnet this large, then the separation between the north pole and the south pole is very large. Right? That means the air gap distance going from the north to south is very large. If the air gap distance is very large, then the magnetic field will come down significantly. And if it comes down very low, then the external stray magnetic field of a current carrying conductor nearby or the Earth's magnetic field can completely demagnetize it, because if it reaches the coercivity point, the magnet is fully demagnetized. That's it. There's no way to build the field back up again. So that's why, first of all, the Alnico magnets are shaped in this weird horseshoe structure so that the north and the south poles can remain as close as possible. Right? Because if you have this bar-like structure, the length of the full magnet, so if you extended this into a full bar, it's going to be extremely large. So the pathway for the flux to close will be very large, so the air gap, which will be lead to very low B field, which can then be quickly demagnetized by stray field. And another thing is, whenever you store these magnets, you'll always put a plate on top of them, so that there is no air gap through which the field completes, but it completes through the ion itself. So if you close this kind of path, then the B field goes back to its retentivity value, 1.25 Tesla. Right? So that means the external fields cannot, there is a significant amount of external field that needs to be applied to demagnetize this closed magnet. If you leave it open, it can get quickly demagnetized. But that's not the case with neodymium, because even in an open neodymium, the field lines is like magnetic field settles down to like 0.95 Tesla or something like that. So neodymium magnets, you get these bar shape because even with the large air gap, external fields are not strong enough to demagnetize it unless you intentionally put it in like a motor or something and pass current in the opposite direction, which can be large enough to demagnetize. But Earth's deep magnetic field or current carrying conductor nearby is no way going to affect it in any way. Right? So, anybody know what the name of this plate is called? It's called an armature. Anybody heard of the name anywhere else? Where?
Motors.
Rotor. So in a motor, DC motor, we call the rotor the armature because in the DC motor, the stator magnets, in many cases would be Alnico magnet. And if the rotor is not present, then there will be a large air gap between the two magnets, one on the left and one on the right, that will demagnetize it. So the rotor plays the role of an armature plate with the magnetic pathway being reduced because of the rotor structure. That's where the rotor name is called in a DC motor armature too. It comes from the Latin word armatura, which basically means armor for protection. So that's why it's called armature, and the rotor for a DC motor is also called an armature. Right? Anybody has any questions? Yep.
You have to worry about the decrease in field strength in, like in motors? Like, is that something you have to model or you ever care about?
It is. So that's the reason in a motor we want to make the air gap as small as possible, right? As tiny as possible. You want to have bigger, the higher powered motors would typically have like very tiny air gap. 0.5 millimeter is a good number. Smaller power, you can go with a larger air gap. But the reason we want to go to smaller air gap is because that magnetic field starts to exponentially drop, particularly like permanent magnet synchronous motors. That's one of the biggest problem, right? Why we use interior permanent magnet. When you have surface permanent magnet, you need a little bit larger air gap because once it rotates, it can get pulled out and so on and so forth. So yeah, that's a very big design challenge that needs to be addressed. Any other questions? Okay. So there's one more topic we need to cover. So Alnico, if you look at the slope, how do I figure out the relative permeability of this Alnico material and relative permeability of neodymium? Do magnets behave like ferromagnetic material when it comes to their relative permeability, or do they behave like air gap? Take a guess. There are only two answers. There are no wrong answers. Both the cons.
Ferromagnetic.
Ferromagnetic. It's somewhat intuitive, right? Like the things that you have put in your neodymium magnet is iron. Known ferromagnetic material. Cobalt is the only thing missing. But it should be ferromagnetic. But that's where intuitions most of the time ends up being wrong. It is not. Magnets do not behave like ferromagnetic material. In fact, Alnico behaves like somewhat ferromagnetic, while neodymium behaves like an air gap. So let's see what happens. So in case of our Alnico, how can we find the relative permeability mu r? Slope, perfect. So if I look at the slope of this, let me just for simplicity assume that it's somewhat linearly falling in this region. So over this portion where it falls and where the magnet operates, it falls at quite a rapid pace. So if you do the difference between the B field here and here, so whatever this value is, minus 0, and then whatever the H field is here to here, that value comes out to, so delta B divided by delta H, because our B equal to mu naught mu r times H, right? So if I do B by H, that's going to give me mu naught mu r. So that comes out to roughly around 100 mu naught, right? So it is not as good as a ferromagnetic material, like pure ferromagnetic, like an iron that we use in motors, right? Around 6,000 would be a relative permeability. In this case, the relative permeability is around 100 to 200 for an Alnico magnet. Still better than air gap, of course. So for our most consideration, when we use Alnico, we can consider it to be same as iron. But if you look at your neodymium, the slope is rather it does slope linearly. And if you do delta B by delta H, so that's 1.25 minus 0 divided by current both H going from 0 to negative 950. So 950 kiloampere per meter, so 950,000 minus 0. This comes out to very close to 13 into 10 to the power minus 6 Henry per meter. And mu naught itself is roughly 12 into 10 to the power minus 6, 4 pi, right? Henry per meter. I'm not sure if it's Henry per meter or Henry meter. In any case, so L equal to mu naught n square yeah, it'll be Henry per meters because the meter square is meter. So yeah, this is correct. So if you look at the mu naught mu r term, so this is the mu naught mu r for neodymium magnet, that is very close to the mu naught of air gap. Right? So neodymium magnets do behave like air gap. So that's a very big problem when we do motor design. You need to be careful when we calculate the air gap length and so on and so forth. When we look at the field lines, we cannot assume the magnet to be an iron material and assume that the field lines would prefer going through the magnet. In fact, the field lines would prefer equally going through the magnet as it will prefer going through air gap at that point. So depending on the magnet, that situation changes. Okay. So there's one more topic called, so let me do all the equations. So we had our BG equation, which was BG equal to mu naught times Hg, which in turn was equal to negative because Hm Lm was equal to negative Hg Lg from our integrated equation. So if you substitute for Hg there, my result being Hm times Lm by Lg. We also had another expression for Bg, which was Bg Ag is equal to Bm Am, which implies Bg is going to be equal to Bm Am divided by Ag. Let me take the product of the two terms, both this expression and this expression. They are both the same Bg. So Bg times Bg becomes Bg squared. This product times this product becomes minus mu naught Hm Bm Am Lm Ag Lg. Anyone want to take a guess as to why I wanted to look at the Bg square? What does the Bg square represent? We have seen that expression somewhere before.
Does it relate to energy?
Energy. So if you look at our energy density, that was Bg square divided by 2 mu naught. Right? What we want to do in our motors and everything is to maximize how much energy we can pass through the air gap. That's the sole objective of our motor design. So that we can push as much energy to the air gap so that that energy can then go to the rotor and then rotate your mechanical rotor. So there is so if we want to maximize this, what is AM/Lm going to be? The cross-sectional area of the magnet times the length of the magnet is going to give you the volume of the magnet, right? We are considering a rectangular structure for the magnet. If I look at the cross-sectional area, this area times the length. If it's a rectangular rectangular structure, that's just going to be the cross-sectional area times the area. So this is the volume of the magnet. And this is going to be the volume of the air gap. Right? Our objective as designers would be to minimize the volume of the magnet, because the magnet is the cost of the magnet is based on how much weight of the material you're using. And all of these are extremely rare earth. They're not rare in the sense of not being abundantly available. It's just rare in the sense of the people who are mining it are not giving it. So the volume, we want to minimize as much as possible the weight of the material we're using for our magnets, particularly when it comes to neodymium. So we want to limit this volume that we have AM/Lm, while we want to maximize our Bg value, right? So what can we do? So we have BH curve. This is our magnetic field curve. And we are going to plot different values for this HMBM, right? So let's look at HMBM in terms of so Bg square times negative mu naught Bg divided by AMLS, right? So we want to increase as much energy as possible in the magnet. So HM times Lm would be our energy density of the magnet, because if you remember, U density we derive Laplace as B dot dH, right? So if B is constant, doesn't vary, then it just becomes B times the H. So we want to increase as much as possible this value while minimizing this particular value. So this is going to be our energy product, BMHM, energy product. Right, for a given value of energy project, let's say this is 60 joules per meter cube, you get some particular curve. This is just going to be an inverse curve, right? Because if HMBM, if I tell you is equal to 60 joules per meter cube, then BM is just 1 by HM times 16 joules per meter cube, right? I'm ignoring the negative sign for now. So it's just going to be negative 1 by X curve. And then if I give you another energy density, that's going to be this curve. If I give another energy density, it's going to be this curve. 50 joules per meter cube, 40 joules per meter cube, so on and so forth. So the point at which you want to do, the thing that you want to maximize is this HMBM. And if you figure out where it intersects this curve, that you have the BH curve of the magnet, right? So if you maximize this, you end up minimizing this term, right? So that you can end up maximizing this term. So if you reduce this, the only option you have is increasing this product HMBM. So you want to maximize this as much as possible so that you can minimize this as much as possible. And the way you maximize this is basically have these curves and see where it interacts with your BH curve, and whichever point it hits, the knee point, that is the maximum energy density of the magnet that you have. If you go any other further lower, you will get multiple operating points, right? You can get higher B field, but that does not mean you can transfer maximum energy to the air gap. So having a magnet, so ideally you would think, okay, if I keep on reducing the magnet air gap to all the way very close to zero, you might end up with better performance. That is not the case, right? Because if you end up going to a lower air gap, that means the BG ends up becoming higher. That doesn't mean it is the place at which you get the maximum energy travel through the air gap. Because when the BG increased, the amount of HM you can push also reduced at that point. All right, so it's a fine balance between choosing what kind of value you run your BG at. For our Alnico, that value would be around 1.0 Tesla or 0.95 Tesla. But the problem is even the tiny amount of air gap that will prevent us from going to that particular H field. In case of neodymium, you can get sufficiently good enough air gap and still operate at a point where you can get the most optimal value out of the magnet, right? So, okay, can you tell me if I give you this curve and these set of curves, how will you go about solving it? If I give you an equation for this curve, and this curve, the equation is already given HMBM, how will you numerically solve it? Has anybody done the optimization course, nonlinear, linear optimization? Nobody taken optimization, right? So when you take the optimization course, this is basically an example problem that you'll use for something called Lagrangian multipliers to optimize what point you will be operating your systems at, right? So with that, we are done. This last thing is not there in the homework, for example.